Okay.
All right.
Can you still hear me, Ben?
Yes.
Okay, fantastic. All right. I'm going to stand here in the middle of the room so that Ben can see me through this camera, so he can see you as well, and that I can still see you. It's my pleasure to announce the keynote of today. Of course, Ben was supposed to be here. Unfortunately, that didn't turn out to be possible due to COVID interfering, but he's fortunately been willing to give the talk remotely. So Ben Gamari is working for Well-Typed. He's based in the US, in New Hampshire. He is originally a physicist, but he became interested in GHC already quite some years ago. And he's also working for Well-Typed quite some years ago, since quite some years already. I forgot exactly when you joined, but for a long time, Ben was about the only one at Well-Typed who really did full-time GHC work for quite some years, I think. But I think he's one of the reasons that we now actually have a much, much larger and very strong general GHC team with several people working on GHC, because people are continuously applying to us and saying we want to work with Ben. And so that's I think shows sort of the amount of knowledge and skill in that general area that Ben has. And he's going to talk about GHC today as well. So in particular, he's going to talk about GHC's info table provenance map. But before we get started, let me just briefly announce on a technical level that you're very welcome still to ask questions during the talk. And actually, I think Ben would appreciate that, because it's weird to talk to a distant audience, and it's nice every once in a while to get some sign that the audience is actually there and there is somebody listening. So you're strongly encouraged to ask questions, but please just hold up your hand. I'm trying to sit there and observe the room, and you need to use the cube, because otherwise there will be no way that Ben can understand you. But the cube is hooked up to the input for the call, and then if you use the cube microphone, you will be able to ask a question normally, and Ben will be hopefully able to hear you. But with that being said, I think I'll just hand over to Ben.
Great. Yeah. Thanks, Andres, and thanks to all the organizers for accommodating this remote talk. I wish I could be there in person, obviously. Sadly, COVID had other ideas for me. But I am nevertheless very happy to be able to speak to you today about some work that I think really is pretty much the culmination of several years of work by quite a few people whose names will come up over the course of this talk, and which I think more importantly sort of represents a coming of age of Haskell in sort of a production setting, right? We've had a few sort of sticking points that have been very resistant to solution in the Haskell community. The availability of backtraces, sort of performance, production-ready profiling tools, and these are both happen to be areas where the work that I'm going to discuss today is bears directly, and this work will hopefully improve the status quo immensely in both of these areas. So, and I would like to reiterate what Andres said. This is going to be a fairly technical talk in some ways. I hope to give you sort of not only a sense of what is possible as an end user, but also how this stuff is implemented, what is under the hood. And so, we're going to go into some amount of detail, and that is going to hopefully be helpful for you, not only as sort of a curiosity, but also as a user of GHC. But in order to make that work, I think it'd be great if people would ask questions when things are unclear, since it's sometimes hard to judge what is clear and what is not. So this is essentially going to be a talk of 4 parts. We're first going to start with a bit of background on how GHC represents objects internally, and how precisely things look on the machine. We're then going to examine this new technology that I'm talking about today, this info table provenance map, and how it can be used for profiling purposes, for heap profiling in particular. We're then going to look at the same map and see what it can do for us with respect to the collection of backtraces, and then finally close with some comments on work coming hopefully in GHC 9.6, which will allow us to attach backtraces to everyday common exceptions. Any exception that you might throw can have a backtrace, just like you would expect in Java or Python, most other languages. And I think that's really sort of the cherry on top here for all of this work. So first, to get this out of the way, what is the info table provenance map? Well, essentially, it's a mechanism for relating info tables, which is a detail of GHC's evaluation and execution model that we'll discuss in just a moment, back to the source construct from which the info table arose. Right? And so the feature was introduced in GHC 9.2 with relatively little fanfare. But we've since then been realizing more and more that there's actually a lot of uses for this sort of information. And so we've been refining and extending this mechanism in each of the subsequent releases, and this will continue in GHC 9.6. Now, to see what an info table is, we need to know a bit about what GHC's heap structure looks like. And this may or may not be common knowledge, so I'm going to quickly cover this. So to look at this, we're going to use this simple program. It's obviously not a program that most people would write in this particular form, but this is essentially how core looks in GHC. When you're going to compile a program without optimization, you often will get these bindings that are very simple, just an application of a data constructor to some payload, and thunks similarly. And so you have, in this particular program, two bindings, X and Y, and X is a data constructor application, an application of the iHash constructor, which you may or may not know is the data constructor associated with GHC's boxed int type. That's the int as you usually use in your everyday programs. And it has exactly one field, right? It has an unboxed number that is the integer that the closure represents. And then this Y binding is, of course, a thunk. If you compile, of course, without optimization, right? It's a good chance that if you do compile with optimizations, that the thunk will be evaluated eagerly, but we're going to put that aside for a moment, assuming that we're not compiling with optimizations. Y is a thunk, and sort of captures a suspended computation, the application of this function frobble to the binder X. Okay. Now, as GHC compiles such a program, it's going to emit into the binary code that it produces a set of static data structures, read-only data structures, that are there primarily for the benefit of the garbage collector. These are known as info tables, and they contain information about the various closure types in the program being compiled, right? So in this case, for instance, we might have two info tables. We would have one corresponding to the thunk Y, which is going to contain a bit of information about Y. It's going to say that, oh, these such closures having this info table are thunks, because Y is a thunk. And the payload of this thunk has no non-pointer fields and one pointer field. And these fields that we're referring to here, in the case of a thunk, are the free variables of the thunk, right? So in this case, we see that Y in its right-hand side captures a reference to the binder X. So this expression is, X is a free variable of this expression. And therefore, we have to make sure that when we suspend this computation, that we somehow keep a reference around to X, since X is necessary to evaluate this computation, to actually perform this evaluation. Similarly, we'll look at another info table for this iHash constructor. Unlike Y's info table, however, this iHash constructor's info table is actually going to be defined in the module where iHash itself is defined, which is, of course, going to be in the ghc.types module provided by GHC prim. This is something that ships with GHC. But regardless, it's an info table of the same sort of shape. It will say that the closures of iHash with the iHash info table are constructor applications, and they have one non-pointer and 0 pointers, right? The non-pointer corresponds to the payload of the iHash, and there are no non-pointers. Okay, great. So this is all static data that the compiler is going to emit. Of course.
Yeah. Can I just start by asking questions myself? Why is there a pointer to X but not a pointer to frobble?
That's a really good question. Yes, so it's assumed here that frobble, this is a surprisingly tricky point, actually. It's assumed here that frobble is a top-level non-calf. So you may be aware that there are these things known as constant applicative forms in GHC programs that are things that essentially are top-level funcs and consequently require special treatment from the garbage collector. So if this were a CAFy thing, if throbble were a CAF, then indeed this thunk would need to retain a reference to throbble, although it wouldn't be in the payload of the thunk. For efficiency purposes, we put this in what's known as a static reference table, this reference to throbble. But regardless, if throbble is not a CAF, so that is, it is just a function, it doesn't have any reference to any other, any thunks, any other top-level thunks, then there is nothing there for the garbage collector. The garbage collector does not need to trace the reference to throbble. There is nothing to be retained from the garbage collector's perspective. And so since these info tables and the thunk layout in general is designed such that the garbage collector can safely determine what values are reachable, there is nothing reachable. Throbble is not something we need to worry about because we're not going to reclaim throbble if it's not a CAF. The garbage collector cannot free it, and therefore it doesn't need to worry about marking it or evacuating it. So that I'm not sure that may be too deep of an answer to that question.
Well, even I think just generally saying that, yeah, it depends on what exactly throbble is and so on and so forth. I think that helps. Yeah, thank you.
Okay, yeah. Now, of course, so this is the static part of compilation process, right? Now, this is what GHC emits. But after we've compiled the program and then start to run it, we're of course going to then enter the dynamic phase of the execution of the program. And in this case, we're going to see that this program is going to allocate two closures on the heap, right? These closures are represented in this bluish color, and they are going to be allocated in RAM, right? They're unlike these green info tables, which are in the executable image itself, the binary code that the GHC emits. These things are actually dynamic values that are allocated and freed dynamically. And each of these closures consists of, has sort of a common shape, right? So in the case of X, X is going to start with an info table, a pointer to an info table, which is going to identify the thing that heads X's right-hand side. So in this case, X is a application of the iHash constructor. And so the info table that it carries is the iHash info table. And then it has 0 or more payload fields. And so in this case, integers have one non-pointer payload field, and so it has one non-pointer payload, and that's the number being represented. Similarly, Y is going to start with an info table, just in the same way as X did, right? This is the theme here, is all heap closures, heap objects in GHC Haskell have always start with an info table pointer, and then are followed by some number of payload fields. And so in this case, of course, its payload is going to be a pointer to X, because X is the free, this is the free variable that we need to that this expression captures. Okay, so that's relatively, so the key insight here is that all closures have info tables, right? I have a corresponding info table that sort of describes their shape, and that these info tables are primarily there for the garbage collector, but what we don't show here is there's a bit of extra information in the info table. In principle, like these constructors, for instance, will carry the name of the constructor. We try not to make info tables too big, however, because they are very hot data. They're accessed extremely often by the garbage collector. And so consequently, for cache residency purposes, we want to keep their size as small as possible, ensuring that we can fit as many of them in cache as possible, and therefore, hopefully, the garbage collector will run more efficiently. So we do try to, so we don't retain a lot of information in the info table, really just the bare minimum of what is necessary to understand, for the garbage collector to understand the heap, and a bit of information to identify objects to the human that is using the program. So great. Now, so if we have this heap structure and we want to profile it, we have our program, we find that it's using too much memory. This is, of course, focusing on heap profiling, not to be confused with time profiling. We're not going to cover time profiling here. We generally, a heap profiler is a tool that allows us to ask and answer, hopefully, a few questions, right? First is, how many of each object type exist on the heap? And how we define object type depends upon our use case, right? We may want to count how many just constructors there are, or how many maybe values there are, or how many thunks there are. But regardless, given a particular definition of object type, we can somehow count how many of each object type exist on the heap. And this is generally pretty easy. This is something that we can do with little more than the machinery already available to the garbage collector, because the garbage collector already needs to know how many objects, or needs to know how to trace through the heap. It needs to be able to traverse all of the closures reachable in the heap. So that's relatively easy. Then the second question, of course, is how much space do each of these object types take? And that's something that you can usually derive from the answer to the first question, right? You take the number of objects of a particular type and multiply it by the size of that object type, of an object of that type, and well, then you have the size that the sort of aggregate size. And that's usually the thing you care about, right? You don't care about how many maybe values you have. You care about how much memory of your poor client's computer are you filling with con cells, right? So fine. But then this third question is really what is necessary to make the answers to the first two questions actionable, right? You need to know where were these things allocated, or at least have some idea of where they arose from, right? Even if you don't know concretely in the program, the exact line number, you want to know at least vaguely how they arose. And of these three questions, 3 is by far the most challenging, because you have to have some way of being able to tie back the dynamic state of the program, the state of the execution of the machine at a particular point in time, back to the source program that you wrote. And there are many, many steps sitting between the state of the machine at some moment in time during execution and the source program that you wrote. You have an entire compilation pipeline, and moreover, you have the fact that if we look above in the heap structure that we saw up here, we don't really have any place to record sort of the provenance of a particular heap closure, right? We have an info table, and I said that does record like the name of a data constructor, for instance, but that's kind of it. They really don't have the any natural place to put information of the form, from where did this arise? So for this reason, GHC has long had this notion of cost center profiling, right? We have this additional compiler mode, which will augment the heap representation to give us space to track information of provenance. Where in the source program did particular heap objects come from? And so essentially, we represent locations in the cost center profiler as, well, as the name would suggest, these things called cost centers, which essentially are just lexical scopes that you can insert either explicitly into your program using these SCC pragmas, or implicitly, or asking GHC to do this automatically with a number of flags that GHC you can ask GHC to insert SCCs in various points in your program automatically. But the point is that dynamically at runtime, the program is going to keep track of the current stack of the current cost center stack, the set of cost centers under which execution is currently proceeding. So in this case, for instance, if we are in this let here, we're going to be executing underneath the hello cost center. And so consequently, when we go to allocate X, we're going to record the current cost center stack in X's closure. Right, so not only is X going to carry with it the usual info table and its payload, but it's also going to carry a pointer to this cost center stack, this red object here, which is going to be a list, a stack of all cost centers, which covered the execution that resulted in the allocation of X, and the same for Y. Right, so both X and Y are going to have a cost center associated with them, and then the profiler can go and use these, and each of these cost centers have source locations as well attached to them. So we can sort of get some insight into where allocations are occurring. Of course, as I said, cost centers are form a stack-like structure, right? So if we insert a second cost center into our program here we have hello, which covers the allocation of X, and then world, which covers Y, and Y is also, of course, because of lexical scoping here, covered by hello. Then we're going to get a heap similar to this, right, where Y has 2 cost centers associated in its cost center stack, X just has hello. Okay. In addition, there's a bit of additional metadata that we track in the info table. Allows us to reconstruct things like the Haskell type of values, but we won't really discuss this too much. And this is a very useful mechanism, right? This is for a long time was the only real way to profile your program, especially from a heap perspective. It's generally quite precise. You can insert as few or as many cost centers into your profile, into your program rather, as you desire, as you need for a particular program, and you can really surgically add these things, which is great. But it's also, to some extent, necessary that you're sort of careful in adding cost centers, because unfortunately, the cost center profiler does tend to have, for better or for worse, a bad reputation with respect to hiding optimizations from GHC. And the reason for that is that GHC tries very hard not to shuffle around these cost centers as it optimizes your program. Now, this is something that can be actually quite bad, because there are many types of programs, particularly those that rely on, say, stream fusion, that rely pretty critically on optimization to achieve the sort of runtime behavior that one would expect. And so if you insert, for instance, in the case of a program that uses stream fusion, a cost center between a producer and a consumer, then you can very easily break the deforestation that you would expect the stream fusion library to perform, and consequently change the space complexity potentially of your program. And that's obviously quite bad, since really you want to be sure when you're profiling that you're actually profiling the program that you're going to be running in production, not something that differs substantially. Thankfully, this is actually somewhat mitigated by another addition that we won't really discuss here, but in GHC 9.2, I believe it was, the addition of the fprof late flag by Andreas Klemmiger, one of my colleagues, which mitigates this by moving the addition of cost centers later in the compilation pipeline to ensure that they don't interfere with optimization. But we're going to put that aside for the moment, because there are a few other issues with cost center profiling. Right? You have the fact that heap size is increased, not just by the one word. We saw up above that each of these closures now has a cost center stack, but it also has an additional bookkeeping word that we need to include in each closure as well. We don't show that here for simplicity, but essentially each object is going to grow by 2 words. And so if you have a just value, right, a bunch of just values floating around your program, those would, without profiling, be 2 words. But with profiling, they double in size to 4 words. Con cells go from 3 to 5, et cetera. It's a rather significant increase percentage-wise in the size of the heap representation of your program, and that can hurt. It's not ideal. And of course, then there's also the binary size increase because of the information that I made reference to earlier in the info tables. And perhaps most importantly of all, this now requires, because of the above sort of limitations or costs, most users in production are really not willing to deploy profiled executables to production. Right? And that's something that is pretty understandable given the above. But it does mean, though, that then you need to specially compile a executable and deploy it if you want to profile in production or anything resembling production. Right? There's a sort of this extra step, which can often pose some significant logistical challenges to the user trying to perform this profiling. And so we really want a way to profile normal executables without compromising performance, but ideally keeping the same sort of, roughly the same precision in the resulting profiler that we expect from the cost center profile. So a few years ago, Matt Pickering and I were sort of throwing around ideas of this nature. What would such a profiling mechanism look like? How might we achieve this? And sort of, if you look at this picture that we have previously on the left here, the cost center profiler inserts profiling metadata in each closure. Right, that seems like a natural place to put it, to put this metadata, because such metadata is sort of a closure specific. Each closure has a particular allocation site that may not match that of any other closure, but it means that we suffer from the issues noted above. So maybe instead, what if we rather put the profiling metadata in the info table, right? We rather say, okay, well, every object has an associated info table, so maybe we can just attach this in some way to the info table, right? The source location, for instance. So this is something that you might be wanting to attach to the info table, the Haskell type and the module that defines the thing. All of this information, you might just say, we stuff it in the info table. And that seems like a fair idea at first. Although, as I said earlier, info tables are very hot data. whereas most of this sort of provenance information, these source location and type and so forth, this is all going to be fairly cold data, right? You don't actually need to refer to this information all that often. And so consequently, maybe it's actually better not to put it in the info table, but rather to put it in this auxiliary data structure, which we place alongside the static info tables in the compiled code, but doesn't sort of not interleave with them in sort of a separate area of the executable where they won't take up cache. And moreover, where we can choose which subset of info tables we want to emit provenance for. This sort of information is fairly large. There are a lot of info tables, and strings of this form are rather take a fair amount of space. So if you add provenance information for every construct in your program, you're going to end up with a fairly large executable. Maybe you only care about a few libraries in your executable. So by having this auxiliary map, just a set of key value pairs, hash map or something like this, and some mapping, you can choose, it doesn't need to be a total map. You can include provenance information for some constructs, but not others. Now, of course, so in this case, we see for this program that we've done exactly this, right? We have we show this info table provenance map, which includes various information tying the info tables back to their provenance in the source program. And that's great. Except for the fact, if we look down here at the iHash constructor, which you'll remember, iHash is a constructor that is defined by the GHC prim package. And data constructors have unique info tables, right? Every iHash constructor refers to the same info table, which is defined in GHC prim. And that its source location is therefore going to sort of be that of the definition site of the iHash constructor. And that's not terribly useful, right? Ideally, we would like to know it's the iHash constructor application that was allocated here in X, right? It's that one in particular, not just, so you want to be able to distinguish between constructor applications. And so this simple, we map info tables back to their provenance approach sort of gives that possibility up, right? We don't really, since constructor info tables are unique. But maybe it doesn't, right? Maybe we can think of a way to work around this. So, and indeed, it's actually not that hard. If we realize that info tables are really just there for the benefit of the garbage collector, as we saw previously, and ultimately, the garbage collector doesn't care whether there's one info table for iHash or 10,000, right? All it cares about is the information within those info tables. And so what we can instead do is say, okay, well, maybe we don't use the unique info table for iHash that we produced when we compiled GHC prim. Maybe instead, every application of iHash can get its own info table, which then can have its own provenance in the info table provenance map. And this is something that we actually allow. This is a very useful tool for profiling. It's enabled with, but we do put it behind a flag, right? We don't want to do this by default, since these info tables, as I said, are rather hot data, and having more of them is going to compromise performance to some extent. Not horribly, but noticeably. So really, so this is the sort of gist of it, right? We have this data structure called the info table provenance map that allows us to map from heap objects, essentially, or rather their info tables, back to the source construct that gave rise to the constructor or thunk or whatever kind of heap object it is. And so to use this mechanism is, again, introduced in GHC 9.2. We have two flags. We have this info table map, which enables the production of the info table provenance map. This is something that, again, it does not do the distinct constructor table trick that I described in the previous slide, but just emits, for things like thunks, you'll get unique, useful source locations out of the info table provenance map. So it's opt-in because, again, it can be fairly large, but not larger than debug information of any other sort. It's just something you obviously want to be optional. If you're going to ship binaries to end users, you probably don't want to enable this. And then this second flag, also available in GHC 9.2, then enables the emission of distinct info tables for data constructor applications. And this is a rather larger increase in executable size, but it can be very useful in profiling for the reason that we saw earlier. And so then in addition, we have a profiling mode based, also present in GHC 9.2, based on info table provenance, right? This is the -RTS HI profiling mode. And we won't actually go into the details of this particular mode. There's actually already a great blog post written by my colleagues, Matt and David, on this very topic, which goes into how to use this and generally its strengths and weaknesses, and how to use event log to HTML, another great contribution of my colleague Matt, to understand such profiles. It's a really great post, and I think it's a really great tool in general. Hopefully you'll find it useful. And
there's a question, Ben.
Great. Yes.
I have a question. When you generate distinct constructor tables, you can't just encode the source locations into the symbols themselves. So why would there need to be a separate map beyond these symbols?
That would be a encoding source location information, especially given that we don't just want a source location, right? We may also want a type and module information. We want potentially quite a bit of information about the provenance of this thing. I think is well beyond what you'd expect a linker to be able to handle in C++. C++ symbol names already, they're not fun for linkers to deal with. There's a reason it takes so long for C++ programs to compile and link. It's something that you really don't want to stretch any further than we already do with, we include already a fairly long hash in the unit ID, and that is included in the symbol names, and then a Z encoded. The symbol names are already fairly long, I guess. So, moreover, accessing symbols, symbol information, it generally tends to be quite platform dependent. And this mechanism here is completely contained by GHC, and that has the advantage. And we already had, as we'll see, a great way of actually capturing source location information on Linux in particular via dwarf debug information, right? But this actually saw relatively little usage, in part because it's very platform dependent. So if you're a Mac user, for instance, you don't get access, you don't get to play with that particular toy. And so having sort of, I've since come around to, there's value in, well, we have to implement more in GHC, having a GHC specific approach to answering these sorts of questions has the advantage that if it runs on any platform, it runs on all platforms, right? And that's very valuable, I think. It makes it much easier to rely on.
Yeah, that makes sense. Thanks.
Yep. All right. So, right. So this is
There's another question, Ben.
Of course. Yes. Yeah. Sorry.
Yeah. Wouldn't having these distinct constructor tables also destroy the cache?
Yes. Yeah. Exactly. That's why it's optional. And that is why there is a you really should probably use this in production sparingly. It is a great tool for profiling, and if you need, in development, for cases where you want to profile, you can't use the cost center profiler for whatever reason. But you're in a development setting, and you need to be able to profile your application, and that there's a leak of constructors. Then distinct constructor tables can be very useful in some modules, right? I probably wouldn't enable this in your entire build though, because as you said, it is going to change the cache. I mean, maybe in development you don't actually care about cache characteristics, right? I mean, you care about heap usage, not necessarily cache, the raw speed of your program on the machine. So maybe maybe it's fine actually to enable in a development setting, but certainly in production I would not recommend enabling distinct constructor tables universally for that exact reason.
Okay, thanks.
Yes.
Any other questions while we're at it? No. Okay.
All right. Here, I'll actually give me one moment. I'm gonna need to call. All right. So. All right. So for the rest of this, and so then there's also this great, in addition to the profiler, there's also a great Haskell interface for getting access to this sort of information, which is somewhat strangely, and I think we might revisit this decision, but exported from ghc.stack.ccs in base, which is CCS here stands for cost center stack. We're where from doesn't really have anything to do with cost center stacks. So we'll probably change this in 9.6. But regardless, this where from function allows you to look up the info table provenance of an arbitrary closure, right? So if I have an object in hand and I want to know who allocated it, what sort of thing it is, what type it is, etc., then I can simply call where from on it. And if there is information about the info table that that object bears in the info table provenance map, then you'll get a just back with that information. And so that can be very useful. And it'll be very interesting to see what people do with this. There's a lot of, I think, a rich space of possible user space profiler, sort of bespoke profiling tools that maybe are more application specific. So we'll see. Very interested in hearing what people think of with respect to using this interface here. All right. So regardless, with the rest of this talk, I would actually like to switch gears a little bit and discuss a problem that I think we've probably all encountered once, if you're lucky, or probably much more. That namely, you spend a good day writing your program, carefully crafting it to use all of the abstractions and techniques that GHC avails us. So you rely on the type system heavily to ensure type correctness by construction of your program, rely on safe concurrency primitives, and try to encode as much as you can into the parts of your program that can be checked statically by GHC. And so you go to compile your program with a smug look on your face, knowing that it's going to run the first time, and go to run it, and oh no, an exception, right? And this is not only frustrating because, well, your program didn't work as you expected it to, but it is also incredibly frustrating because now I don't even know why, right? I have absolutely no lead on how to approach this problem. I know that head was called somewhere with an empty list. And well, I mean, I don't know where that could be. It could be my own code. It could be in any of the million lines of transitive dependencies that it depend upon. It could be buried within multiple layers of transitive dependencies, right? This is a pretty bad state of affairs, and generally is the beginning of a pretty bad day, right? So in GHC 7.10, we of course introduced this mechanism, has call stack, which allows us to essentially build a call stack and maintain a call stack in user space, essentially, in Haskell, that with the help of the constraint solver. And in GHC, I believe it was 9.0, we finally gave in and just added has call stack constraints to many of the functions in Prelude and Base, which arguably shouldn't have been there to begin with, but are not total. And so now, as of today, if you encounter this issue, you'll see an error closer to this, right? You'll see that head get the same error, but then you'll also get a call stack, which unfortunately, may not actually be all that helpful because you may only get one level of stack information, right? If the libraries that you're depending upon, that perhaps one of them contains the bad call to head, if these libraries don't include has call stack constraints themselves, then well, you'll get a truncated call stack. And so, you'll be forced to either just stare down the issue or sort of work your way up the call graph and add call stack constraints one layer at a time until you make it back to your own code, and at which point you can start debugging. And so this is not ideal. It's a frustrating process, and from the perspective of somebody coming from outside of the Haskell community, your Haskell or your Java user or your Python user, this seems very strange, right? This is something that most languages take for granted, right? You can always get a call stack. This is something that's ubiquitous and something that you would expect the language runtime to deal with. You shouldn't need to emulate this in the source language. And so for a long time, we've been wanting to address this, right? And indeed, in 2012, Simon Marlowe at Haskell Implementers Workshop gave a talk entitled, "Why Can't I Get a Call Stack?" And unfortunately, beyond the has call stack constraints and perhaps the dwarf work that that Peter Wortman we wrote his thesis on, that is now present in GHC, it's largely, the state of affairs is largely unchanged, right? Not much you still pretty much, if you're not able to use dwarf, which relatively few people are, you're probably not able to get a call stack beyond what has call stack is able to get you. So I was thinking about this a while back, and with the help of Sven Tenney, who did a lot of work in the early prototyping of this. Well, yeah, okay, of it helped addressing the early phases of this task. Realized that, well, stack frames are actually very, very similar to heap objects. And we already have a way, a mechanism, via the info table provenance stack, of identifying the source provenance of heap objects. So maybe we can simply reuse that machinery for stack frames as well, allowing us to unwind the stack and provide useful source locations for the result, the unwound stack. So to see how this works and to sort of be able to understand a bit of how what's the stack means in Haskell, right? Because many people are rather divorced from this concept. It's something that Haskell, unlike many languages, allows you happily to have an infinite size stack. You don't really have to worry about when you're, even if tail call optimization fails, maybe you don't even notice, right? Because you have enough memory to accommodate the large stack that arises. So, and moreover, Haskell is perhaps a bit different than most languages in the meaning of its stack frames, and that's something that you need to sort of understand in order to know how to interpret backtraces in GHC Haskell programs. So we're going to sort of discuss a little bit now about how stack frames arise, what they mean, and how you can understand them. And then we will sort of close this talk with how we can use the IPE mechanism to gather a stack trace, and then how we can attach those stack traces to exceptions. So, all right, the evaluation stack. So, to review the evaluation stack and its meaning, we're going to use this program here, a very simple program, which a function of 2 arguments, which is going to apply a function to its first argument, and depending upon the result of that evaluation is going to do something. It'll return either the second argument or 0. Right? So the key bit here is noting that we have in the right-hand side of foo this case expression. And so the majority of stack frames in your program, I think it's fair to say, are going to arise from case expressions such as this. And the reason is that how does case evaluation work, case analysis work in a Haskell program? Well, you're going to first push a continuation, a bit of, a pointer to a bit of code that will perform the discrimination to the stack is the first thing you're going to do, right? You're going to write down what should happen after the evaluation of the scrutiny has concluded. You write this down in the evaluation stack. Then you're going to enter the scrutiny. So in this case, that would involve calling the isOdd function with its argument x. And then after it's finished coming to its conclusion, right, after isOdd computes its result, it is going to then look at the stack and use the frame at the top of the stack to then jump back to the continuation that we pushed at the outset, right? So in something like C++, which is the intermediate language, and this is sort of pseudo C++, but something like C++ that GHC uses as its intermediate representation, imperative intermediate representation, that would look something like this, right? We have foo, which is a function of 2 arguments. We first push this stack frame, which we call a return frame, since it's sort of a stack frame that we will return to after evaluation has finished. And that return frame has to contain in its payload any free variables that the continuation might require here, right? So the continuation in this case is going to look at the result of the isOdd function, right? And it's going to say if it's true, then it's going to pop the free variable y off of the stack. We get y from the stack frame that we previously pushed. It's up here. And then it will jump to the oh, whoops, actually, sorry, that was actually not quite right. Oops, this should have been a result should be y here, and y should be popped from the stack. I apologize for that. Anyways, the idea here is that when we're inside of isOdd, the stack is going to look something like this, right? We're going to have the stack, which is going to have some frames beneath us, but the thing at the top is going to be a continuation frame, which is going to identify this continuation here, which is going to perform the discrimination of this case analysis. Decide which alternative essentially should be taken, and then compute that to concretely what this continuation is going to do. And the thing to note here is that this stack frame, this continuation return frame, looks very much like a heap closure in that it begins with an info table pointer. And that's very important because the garbage collector, just like, needs to trace stack frames, right? And so that's why we are using the same sort of data structure to record the layout of the stack frame as we do the heap object. We're technically glossing over a few details here. It's a slightly different representation. We use a bitmap instead of the number of pointer counts, but this is a technical detail that we can gloss over for simplicity. So the idea is it still has an info table, which means that we can easily just add entries to the info table provenance map corresponding to these info tables. All right, and so now all of a sudden we now have a way to map from a stack frame back to the source location of, for instance, in the case of a return frame, like the one associated with this case analysis, back to the location of the case analysis that that return frame arose from. So that's very useful because that's sort of the first step in being able to gather a stack frame, right? Now you have the ability to usefully identify stack frames to the user. So then, of course, the only thing that remains is the ability to actually somehow view the stack. And to achieve this, Sven and I implemented a set of primops and a new snapshot data type that will allow you to sort of preserve an immutable copy of the current state of the stack, and then be able to decode that snapshot later on. And this is actually, this snapshot important. We cannot decode the stack in place because, of course, that may require evaluation, and evaluation is going to mutate the stack. So you'd be sort of trying to essentially decode target changing as you're, and then that's feasible. So so we instead, in order to gather a backtrace, you first gather a stack snapshot of the current thread, but we also allow you to gather snapshots of other threads running for monitoring. Right? For instance, you have a worker thread running in your program that you've not heard from a while, and you might wonder, well, you have a monitoring thread that's recording. Oh, well, I haven't heard from him for a while. I wonder what he's doing. And you ask for a stack dump, and that will allow you to then gain some insight into what that thread is up to. But then regardless, after you have a snapshot in hand, you can then decode it to a list of stack frames. Each stack frame is going to include the same sort of information that you'd expect from the info table provenance that we saw earlier in ghc.stack.ccs. Yes, I believe that's right, in the where from interface that we saw earlier for heap objects. Now, there's a few caveats here to interpreting these stack frames. Once we have a stack frame, we need to keep in mind that this is the Haskell stack that we're talking about, not a C-like stack. And so, well, in a C-like language, there's generally a pretty tight one-to-one correspondence between call sites and return sites. So that is to say, if I have a C function that calls f, what is going to be pushed to the C stack is going to be the address to which execution should return, essentially the line after the call to f, right, is what will be present on the stack. So it's in the same way a return frame of sorts, but unlike Haskell, that return frame is almost always very tightly associated with the call site, a particular call site to f. Whereas in Haskell programs, that's actually not necessarily true. There may be many call sites that all return to the same point. And that's in part true because of tail calls, and also just we support zero-cost tail calls, and also just generally true because GHC has a somewhat more general execution model than C. And so the idea here, but to take this example here, a new example, we have these two bindings here, var, which will enter some scrutiny, and then after that is finished, it will return to foo, and then baz, which will as well evaluate something else and then also return to foo. If we see foo on the stack, that could mean that we are in the scrutiny prime or scrutiny, right? We can't tell which one of these we're in. And moreover, if we're in foo, we may not actually see bar or baz on the stack. And I think the way I like to think about this is that in a typical C-like language, or Python or Java, you think of stack traces, you often say that they're back traces, right? The stack is going to capture all of the steps that we took to get to the point where we are currently. Whereas in Haskell in general, they're actually more like
There
forward traces.
a number of questions.
Oh, good. Okay. I'm sorry. I can't see really all that
Yeah.
well, so I
No,
apologize.
that's fine.
Yeah. Don't hesitate to interrupt.
Don't know. Joachim was one, but there was at least one more. Ah, okay.
Hi, Ben. Just a quick checking of my understanding. In this case, I would expect that the continuation in the second case would then also first check the result of the scrutination to see if it's just nothing, and then run
That's true.
through. So this wouldn't really be the same continuation, would it?
That's true. No, I apologize. Yes, that should have been a wild card as well, or some sort of, yeah, that's right. That's right. No, the continuation is, that was a very good catch, Joachim. Yeah, I apologize. This second case actually is distinct because, as Joachim says, after this case, after scrutiny prime returns, well, we first need to make some decision as to what to do next, and that requires a distinct piece of code that may or may not lead to foo. And so consequently, the stack in scrutiny prime is not actually going to contain foo. That's something I should have been more careful here. I took this example from a different sort of morphed this example from another case that I was thinking of, and I guess I hadn't fully pondered that implication. But yes, no, if you change this into another wildcard, for instance, then it's entirely possible that GHC will produce code where the scrutiny will instead return directly to foo.
Okay, thanks.
Yeah, okay. That was the only question, actually.
Okay, great. Okay. So the point here is that, yes, and really the idea here that I think is most important is that, if you're in foo, you don't necessarily know how you got there, right? Now, this isn't in practice that much of a problem, actually, because often you can use domain knowledge of your program to determine how you must have gotten into foo, right? This is function calls tend to be rather local, and so if you're in foo, chances are you arrived at it via some function in its immediate vicinity, or you can use the other frames on the stack to sort of infer. But it is certainly something that you need to be aware of, right? It's not quite as straightforward to interpret these stack traces as you might expect in a more imperative language. So, but if we have a stack trace in hand, now we have we have the ability to collect a stack trace. Now, obviously, being able to address the head empty list problem that we saw earlier, the infamous unidentifiable exception, unlocatable exception problem that we know and know and hate. We really want to be able to attach these backtraces to exceptions, right? That would be the natural way to address this, and that's indeed how most languages manage exceptions. You have a backtrace where you can tells you the cause. So, in order to see how we might do this, we can quickly review our extensible exception machinery, and essentially, it's a rather nice bit of library design, really, since our exception machinery essentially allows an open world of exceptions, right? Users can add new exception types freely, and likewise can freely handle any subset of exceptions that they see fit. And we accomplish this by way of some sort of carefully designed dynamic typing, achieved by way of this some exception type. Right, so this is a type that is going to carry with it some A, and also its exception dictionary. And that exception dictionary is going to allow us to cast to and from the some exception type. Right, so now if we have a some exception in hand, we can essentially check to see whether it's an exception that we care about by using this from exception method. And also, we have the ability to show exceptions for the user, so we can kindly tell them that their program crashed. So we might think that, okay, well, some exception, that all exceptions are ultimately represented with some exceptions. So maybe that would be an obvious place to add a backtrace, right? We can simply just add some sort of type, a field that encodes a backtrace to some exception. And it seems like a reasonable way forward, but unfortunately, it's also it has a few unfortunate compatibility implications. There are a lot of consumers and producers of some exception, and so adding a field like this would probably be a rather breaking change, more so than we would like. And there's also the problem of, well, it turns out that over the years, we've actually accrued quite a number of backtrace mechanisms. So, well, Simon's talk, why can't I get a backtrace, is still we still don't have exception or backtraces on exceptions. We do have a number of ways of sort of identifying to varying levels of precision what the program is currently doing. Right? So these include like the Haskell stack mechanism that we talked about earlier, but that has the downside that it requires changes to the source program. You have the cost center profiler, which may require changes to the source program, and but requires a compiler flag that people are generally reticent to use. Oops, sorry. We have the dwarf mechanism, which is great and allows unwinding through foreign code, which is a particularly handy feature in sort of polyglot environments, but only really supports Linux currently. We love to extend that, but it would require somebody stepping up to provide work or funding. And moreover, we have this info table provenance mechanism, which requires, it works great for pure Haskell code, and which only requires that the user use this f-infotable map flag to enable. But it's really not obvious. Infotable map provenance generally isn't going to be quite as precise as Haskell stack. So if you have Haskell stack, or for that matter, the cost center profiler, then maybe you actually want to use them as your backtrace mechanism, not in the infotable work. Or if you are in a polyglot environment, maybe you want to rather use dwarf. There's not really a one-size-fits-all solution here. And so we really want to be able to capture any of these, all of these, some subset of these mechanisms when we capture a backtrace for an exception. And so when I about a year ago opened a proposal in the GHC proposals process, suggesting essentially something like this here. Just add the naive add a backtrace to some exception approach. Not necessarily because it was a good proposal, something that we would want to implement, but it was a good starting point. It was something to begin discussion. And indeed, it achieved that end quite well, I think. So there's a few users, Matt Parsons in particular, had some excellent insights into sort of stemming from his own experiences in his own commercial code base and working with exceptions therein. And really related the value of being able to annotate exceptions with arbitrary metadata. So for instance, if you're in a server environment, maybe if an exception happens, you not only want to have a backtrace, but you also want to be able to record some information about the request that triggered that exception, such then it can be recorded in the in whatever monitoring or logging mechanism you're using to monitor this system in production. And there are various ways of emulating this in the with the current extensible exceptions mechanism, but they're generally pretty inconvenient, right? Ideally, we just want some way to sort of acknowledging that exceptions themselves are somewhat of a cross-cutting concern, be able to extend the information that an exception will capture with arbitrary metadata. And so the proposal that we came up with looks something like this, right? We have some exception, which is essentially the same as it was previously, except it carries this one extra context that is an implicit parameter, right? The same mechanism that we use to implement Haskell stack, which captures an exception context, right? And this exception context is essentially emulating the dynamic typing approach that some exception itself uses, right? It captures a set of annotations, each of which are simply existentially quantified over with a exception annotation class instance, dictionary, which really only contains the ability to display the exception to the user, right? And so this is generally for use by the top level exception handler. So the idea is that we can take and add, these exception contexts are monoidal, although we can add in any number of ways, annotations that contain, capture the various types of backtraces that we have. And moreover, the end user, can extend this further, including other information that's relevant in their own domain to the exception. And this includes things like, the cost center so in the case of backtraces, we would have, types for each of these backtrace mechanisms. They would each have an associated exception annotation instance, and they would all be printed as appropriate in the display exception annotation method of this instance. So that's a really that's sort of the current state of the proposal. Then the idea is we further augment the throw functions that base provides to capture backtraces when an exception is thrown and attach them as annotations. And so this is a relatively two almost orthogonal proposals here at this point, right? We have this exception annotations mechanism, and then we also have this implementing a number of annotations for backtraces and capturing those backtraces in the throw function. Likewise, we also need some way of choosing which of these we want to collect. Some of these can actually be quite expensive to collect. Dwarf, in particular, is a rather expensive one, and even this info table provenance backtrace requires capturing a snapshot of the stack, which if your tail call optimization has failed, or if you write a program that is not tail recursive, then you can easily build up very large stacks. So that capturing that snapshot may be costly. So we want a way to be able to select which of these backtrace mechanisms is used. And so with the pragmatic approach that the proposal currently captures is a bit un-Haskell-like. It's a bit of global state shutter, but it is sort of, I think, fits with the fact that these things are sort of cross-cutting concerns that are more, in an ideal world, we wouldn't need to choose. We'd be able to capture them all, or we'd have one mechanism that sort of works well in all cases, but that's just not the world we live in. So we have this sort of pragmatic global state that we can use to enable and disable individual backtrace mechanisms that throw will use to capture backtraces when an exception is thrown. And so there's actually a prototype implementation of this up on GitLab. It is currently able to capture all of the 4 backtrace types that we described above and attach them to exceptions when thrown. And so the output you get, if you enable all of them, is pretty pretty significant. You don't even see much of the others, actually. Most of this is taken up by the dwarf backtrace, but regardless, it's actually quite useful, and you get useful source locations in each of them. It's actually quite promising, I think. So in sum, in this talk, we discussed both the info table map, a bit about the implementation, how under the hood, how this mechanism works, as well as its uses in profiling and provision of stack backtraces. The info table map work is available in 9.2, and stack snapshotting is available in 9.4. The exception work is going to appear in 9.6 with luck, although we still have yet to get the proposal through the proposal process. And as always, having more feedback on that proposal will always help. So if you do have time, inclination, please do have a look at the proposal and offer your thoughts. We also, as I sort of mentioned at the outset, continuing to refine this info table provenance mechanism. I currently have the metadata that it emits is actually quite large at the moment. It significantly increased binary size. I have a patch which will hopefully be merged in time for 9.6, which should cut that roughly in half, if not more. So that should make it a bit less onerous, especially if you're deploying these so instrumented binaries to end users who tend not like 100 megabyte executables. Of course, there's several acknowledgements here. I think I probably mentioned all of these people at some point during the talk, but Matt Pickering has been instrumental in his work on info table provenance in particular and profiling more generally. He's really pushed the ball forward immensely in this area. Sven Tenney has been doing great work in the stack unwinding, the implementation of the unwinder, and some of the initial work prototyping the exception backtrace mechanisms. Matt Parsons, obviously, for his feedback on the proposal and really helped guide the library design in a much more useful direction. Vlad has been the shepherd of the proposal and has been also very helpful in reviewing and pushing the proposal forward. And finally, Hazura has been very helpful in supporting our work within well-typed on profiling and related work. So I think they deserve a shout out here. And as well, Andreas, for also similar work in profiling, Andreas Klabinger. So thank you to all of them, and thank you for your questions and listening. I'm happy to take more questions now, or I'll be on IRC for the rest of the day. So don't hesitate to reach out, and Slack as well for that matter. So do look forward to hearing from you, and thank you for listening.
Yeah, thank you. And we do have questions. Yeah.
Great.
So another very useful debugging mechanism is heap inspection. Would it be possible to take the backtrace, any of them, and inspect the thunks?
Yeah. No, this is actually a really interesting opportunity indeed. So you may be aware that there's this GHC debug project that we've that Matt and I and within well-typed, but many of us have been sort of working to push forward, which allows you essentially to inspect the heap with any given heap object to introspect on its structure. And stacks would be a great way to extend that, and allowing you not only to get a sense for where the program is in execution, but also sort of what values is it working with currently. What if you're what are the free variables of any thunks in your on the heap, right? For instance, and that's something that could well, actually, I think has been done, but we don't really have a good sense of. There's a lot of work in GHC debug to be done that I think there's open questions here. Happy to have people work on them regarding how to actually make this tool usable, because it's really a fire hose of information, right? And the heap can be quite large. Even a small program can have a very difficult heap to wrap your head around. And so the question is, how do you distill the heap representation that GHC debug gives you down into something that is comprehensible to a mere human? Or even if you can't do that, how do you allow the machine to sort of draw some inferences about the structure of the heap and perhaps more automated reasoning about what how it might be responsible for particular either memory usage bugs, profiling tools, or correctness bugs, even by trying to identify a set of objects that the user can then look at more carefully. So I think yes, there's definitely a lot of work there. The current work that is exposed in the branches up on GitLab currently don't really offer any ability to introspect on the contents of particular stack frames, right? You get the source locations and that's about it. But in principle, that could be changed, or you could just use GHC debug. But yeah, it's definitely a very interesting opportunity. Having an interactive debugger for Haskell, essentially, being able to, like you can in most other languages, break into the program and really examine with easily, conveniently, the state of the program is really the goal of GHC debug. So we're much of the way there, I think.
I have a question. The GHC flags that we have been introducing in these talks, they only affect the user libraries, but not the bootlibs. So do we have plans to issue the GHC binary distributions that also build the bootlibs with these GHC flags?
Absolutely. Yeah, that's right. I don't necessarily know that we will do so with distinctive constructor tables. that seems like that might be a step too far. I mean, it's not necessary unless you're debugging base. The distinct constructor tables is really a feature that you want, a flag that you want to enable in the thing that you're debugging. And so that particular flag we probably won't enable, but yes, distributing GHC with the info table map is certainly an option. There's also some thoughts regarding whether it might be interesting to, or productive to, split out the debug information, the info table map essentially, into an additional package that then can be installed alongside GHC, so that they'd be sort of out of band information that that the user can then optionally opt into without downloading a whole new binary distribution. That is definitely appealing, but it also brings with it some complexity, and in particular packaging complexity, which is kind of the worst kind of complexity, right? Now, being able to find, locate the IPE, the instruction info table provenance for a particular module on the file system, if it's not in the loaded image, is actually quite difficult. So it's a bit unclear how to address that problem. And I worry that by, we don't want to compromise the general utility of info table profiling with this desire to make it, sort of more available. If it's more available but also less reliable, then that I think might be a net loss to the community. So I don't know.
So with info table profiling, I guess one risk is that it punishes you for abstraction, because if you hide the constructor of your data constructor under some helper function somewhere centrally in the library, and that doesn't get inline, then you get less context information. Because you only know, okay, it's the one function that happens to be allocating all my I don't know, data map constructors. Is there a way of, like, if I run into this problem and notice, okay, this function has the allocation point for what I'm caring about, but it's called in many places, is there a way of telling GHC, just create many copies of this one function for all use cases, or like inline it into all modules that call it, so that I actually get different call sites? Or are they put differently? Can I get more context information into the info tables if I really need them? Or is that when I should stop and go to normal cost center profiling?
Yeah, that is a good question. You hit upon one possibility here, obviously, and that's inlining. Just rely on usual inline pragma, but that's obviously not ideal. It is a compromise. Yeah, I don't. I'm going to have to think about that. I don't know of a great way of attacking that particular issue. The problem is, beyond inlining, that is, the problem is that, you sort of would require some way of passing information, contextual information around implicitly, maintaining essentially what is a cost center stack in the execution state of the program, which is, at that point, you've reinvented the cost center profiler with all of its, ups and downs. So, yeah, my initial thought might be it's probably a point where you want to use the cost center profiler, but that is not a particularly satisfactory answer, I'll admit. You could, inlining and specialization, I guess, might be the two things that you could rely on to try to separate out these the various allocation sites. Yeah, you could potentially, presumably the things inside your maps are differing, right? So if your map, so I guess really, if that's really the point, you have one sort of funnel function through which all map allocations are occurring. Well, but the things that are being passed, the contents of those maps are presumably different, and those will presumably be distinguishable. So maybe that helps you, saves you as well to some extent. You don't know, you can't distinguish individual map allocations, but you can distinguish their contents. Yeah, but the point's well taken.
Okay, so I think we should also soon come to an end, but there's one final question.
Okay, yep.
it's rather a follow-up. So is it possible to just add cost centers that are different for different call sites to any function? Because that would
Oh,
also
yeah.
solve the
Oh,
same
so that's
issue.
another actually interesting point. A few years ago, actually, I added this caller CC mechanism to GHC, which actually, I think, if I understand your question correctly, does precisely that. It will introduce a cost center at every call site of a function, such that you can, so you can say like, and you can filter, say, introduce every time you see a occurrence of the map function, wrap it in a distinct cost center, such that you can then, well, distinguish the call sites. And that can be very, very useful, actually. That's a really handy feature that I feel like we probably didn't advertise quite enough. But yes, so to answer the question, yes, I think that is possible. Look up, I think it's fcaller CC in the user's guide, and I think that's available in GHC 9.0 and later.
Okay. Yeah. So let's thank Ben again.